Hello everyone, welcome to Multimedia Systems course project presentation. In our CSC561 course project, we have explored cooperative video processing in multimedia IoT systems. I, Sweda Mahfuza Begum, am excited to share our project details with you. Main methods. We thoroughly survey features and requirements of edge video processing for IoT, multimedia IoT systems in different typical scenarios. Generally speaking, there are two conventional video processing methods. The first one is to pre-process source video chunks at the camera node. Video pre-processing, such as extracting features from video frames, would reduce the amount of data to be delivered to the remote IoT server when a transition from the pixel domain to the feature domain is performed. The original source video can be delivered to the IoT server later if needed. The second one is the directly transmit video chunks to the remote IoT server for processing. Drawbacks. However, these two methods would lead to significant delays. The reason lies in the fact that the limited computational resources of video source nodes might incur computational delay when pre-processing video chunks locally. Meanwhile, the delivery of original video chunks to the remote IoT server can result in network congestions and delays due to the long distance or multi-hop transmissions. Thus, it is significant to develop other methods that accommodate the requirement of delay-sensitive video processing tasks for multimedia IoT systems. Motivation. Our motivation is to accommodate the requirement of delay-sensitive video processing tasks for multimedia IoT systems. Edge computing and its related concepts, for example, fog computing and cloudlet, can serve as enablers of distributed computing for the pre-processing of video chunks. By leveraging the edge computing technique, redundant computation, storage, and communication capabilities of multiple network edge nodes, for example, smartphone, smart car, access point, femto base station, and robot, in the proximal can be utilized through local high-speed wireless or optical networks. Thus, the service delay can be reduced when the video processing task is handled at nearby edge nodes. Moreover, delay-sensitive video processing tasks can be divided into subtasks and pre-processed by multiple edge nodes in parallel to further accelerate the computation. In edge computing enabled networks, the handling of video processing tasks for multimedia IoT systems is different from that in conventional networks. For example, the feature extraction from source video chunks is executed at edge nodes instead of at the remote IoT server. Thus, the compression of video chunks, which may degrade the object detection accuracy, is no longer a severe problem since the capacity of local networks is sufficient and lossy compression is not needed. Instead, new problem arises that how to properly assign video subtasks to multiple edge nodes. Related works. In the first work, the author studied a cooperative video processing scheme in an edge computing framework. In the proposed scheme, group formation and video group matching are both considered to maximize the human detection accuracy within the video task's deadline. Furthermore, the optimal matching theorem is demonstrated by using mathematical induction, and a low complex heuristic algorithm is proposed for video group matching problem. In energy delay cost trade-off for task offloading in imbalanced edge cloud-based computing, the jointly offloading decision and resource allocation problem were discussed for the imbalanced edge cloud-based computing offloading with multiple mobile users and multiple tasks per mobile user. In particular, a new metric in counting mobile users and in counting the mobile users' offloading performance such that the delay energy cost trade-off based offloading cost is proposed, in which the ECS excess cost was introduced to characterize the ECS excess delay and the resource using payments by considering different service level agreements between APs and ECS. Both problems of minimizing the sum offloading cost for all mobile users, that is efficiency based, and minimizing the maximal offloading cost per user, that is fairness based, were presented. Since these problems are all NP-hard, the several suboptimal algorithms have been proposed. As it is difficult for single node in wireless sensor networks to run relatively heavy applications by itself in a tight deadline, an emerging system named Cooperative Computing System for heavy computation and low latency processing in wireless sensor networks is proposed. To meet the explosive demand on delivering high-definition video streams over cellular networks, a social-aware video multicast SOCAST system leveraging device-to-device, that is D2D communication, is designed. SOCAST is a cooperative video multicast system based on social trust and social reciprocity. In SAW, the authors proposed a scheme to assign feature extraction tasks to mobile devices through their web browsers while taking into account different capabilities of different edge nodes. In the last one, the authors studied the problem of minimizing the completion time of multiple feature extraction tasks that share the communication and computational resources of multiple edge nodes for task offloading. However, all these studies focused on specific video pre-processing tasks such as feature extraction and lacked practical implementation of various video processing functions at diverse edge nodes in a cooperative manner. As motivated, the main focus of our work is to develop a flexible edge computing platform that implements edge video processing functions, especially for the multimedia IoT system architecture. For edge computing of delay-sensitive video tasks, a video source node, for example camera, visual sensor, can offload its video tasks to nearby edge nodes. For example, smartphones, satellite processors, or vehicle OBUs via local wireless or optical networks. And the edge nodes are within the local communication range of the video source node. The video source node captures video sequences such as video tasks, divides each of them into multiple video subtasks, compresses these video subtasks, and delivers them to edge nodes. Next, edge nodes execute video processing functions, for example, computing SIFT descriptors with the received video subtasks and upload the results to a multimedia IoT server for further video analysis, such as object or event detection. A delay-sensitive video task is supposed to be processed within a deadline and will fail if the deadline is passed. The general model of the edge video processing is illustrated in Figure 1, which consists of three main components, namely video source node, edge node, and multimedia IoT server. The video source node generates video tasks periodically, divides each video task into a number of video chunks or subchunks, compresses video chunks at certain compression ratios, and assigns compressed video chunks among all the edge nodes according to scheduling policies. The edge node is with surplus computational ability and storage capacity, helping pre-process video subtasks, for example, feature extraction. Moreover, edge nodes can form cooperative groups based on specific group formation policy and receive the compressed video chunks according to the video subtask assignment policy. The multimedia IoT server collects the pre-processing results from edge nodes and performs further video analysis, which has abundant computational abilities. We have considered camera node, edge node, and server for our experiment. Performance evaluation. As we are yet to achieve the desired simulation results, we are sharing the performance evaluation in existing literatures. Firstly, a baseline case is considered where the worker is disabled and only the leader pre-processes the video sequence. That means both two video subtasks are delivered to the leader over the wireless channel and there is no cooperative processing. Next, for the case of cooperative processing with one leader and one worker, each node preprocesses one subtask. The elapsed time for container establishing over all nodes, video chunk or subtask delivery for all nodes, task computing over all nodes, and the total time of task completion under different link capacity from the video source node to one edge node are measured. In figure 3, compared to the cooperative processing case with two nodes, the total time consumption of video task completion of the baseline case is much longer. Figure 4 and Figure 5 also show that the cooperation and the proposed scheme outperform than the others. Results. The proposed scheme can bring lots of advantages if deployed in practice, such as reducing the delay, that is reducing the delays of processing the task at the camera and uploading the data to the server. Reducing the cost, that is reducing the costs of uploading the huge data via LTE and is easy to deploy, that is relying on the existing facilities. However, there are also some limitations. For example, the integration of processing results is not considered and the computational ability of each edge node is assumed to be the same. Few improvements. Edge video processing for multimedia IoT systems faces many challenges. The first challenge is that the management overheads of large-scale edge computing-enabled networks could be significant when the number of edge nodes is huge and cooperative nodes are widely spread. The second one is that the distributed edge computing resources should be carefully scheduled to enlarge the improvement of utilizing edge video processing. The last challenge is that the quality assessment of video in multimedia IoT systems is still not well investigated yet. In the future work, we will consider the balance between the energy consumption and the completion time, the dissimilarities of mobile devices, for example, computational power and energy storage, and the actual processing models and video chunks. Furthermore, the problem of minimizing the amount of necessary bandwidth with the minimum acceptable detection accuracy constraint in the future network will also be considered, where the bandwidth and cost are limited. This is the end and presentation. Thank you. Special thanks to Dr. Pan, our teaching assistant Juan, our classmates and my lab mates for their time, support and feedback.